Today I will be discussing the general form for the derivative of tetration, more specifically x tetrated to n, which is defined as x to the power x to the power x to the power x n times. And tetration is right associative, which means you work the powers first and then come down to the base. So if you had 2 to the power 2 to the power 2, you would work the top 2's first and then raise to the worked out value, for instance. So now that we've cleared up how tetration behaves, I want to discuss the derivative of tetration of degree n with respect to x. So basically the derivative of x tetrated to n. What is this? So one approach I want to take here is defining tetration recursively. So let's say f of x is x tetrated to n. I'm going to define fn of x, which is dependent on the previous value, x to the power fn minus 1 of x. And why is this useful? Well, it gives us a recursive derivative, a general recursive derivative. Let's take an example of exponentiation. So f of x is equal to x to the power n. Forgive my x there. But then we can write fn of x is equal to x times fn minus 1 of x, which is a similar formulation for tetration, but now we have x multiplied by fn minus 1 of x instead of x raised to the power fn minus 1 of x. So we can find the derivative of fn prime of x as the derivative of x, which is 1 times fn minus 1 of x, plus the derivative of fn minus 1 of x, which is, we can write fn minus 1 prime of x times x, like that. So this is a recursive formula. Let's test it with degree 2, so x squared. We can write fn of x. I should just write f2 of x, but fn of x works fine for this denotion. Fn prime of x, we can use a formula, fn minus 1 of x. So n minus 1, that's 1, so x plus x times the derivative of n minus x to the power n minus 1. That's just, the n minus 1 is 1, so derivative of x is just 1, so we have x times 1. And the multiplication, that's not an x, let's correct the x, multiplied by the derivative of x, which is just 1 itself. Ooh, software, yeah. And we can see this just works out to 2x, which is, as we know, the correct derivative. Oh, I'm not doing good with this pen today, but it's the known derivative of x squared, which is 2x. And so we know this recursive general form for the derivative of x exponentiated to n works. And we will apply the similar logic to the tetration case. Now we have f of x equals x tetrated to n, which is x to the power x to the power x to the power x, right associative, n times. We work out the top few parts and then work top to bottom instead of bottom to top, which is left associative tetration, another function entirely, n times, okay, no space there, but now we can define fn of x as x to the power fn minus 1 of x, which works out from the definition of tetration itself. So now we need to define fn prime of x, which is the derivative of tetration of x to n. So first, let's write the converted recursive form of tetration, and I want to represent this function in terms of Euler's number. So we have x to the power fn minus 1 of x, and we're going to equate that to e to the power ln of x to the power fn minus 1 of x, but that means the power fn minus 1 of x just comes out to the coefficient of ln of x. That's a badly written ln of x, but you see the idea. And I want to make a little side note over here regarding the general form for the derivative of f of x equals e to the power g of x. So say we have an f of x that's equal to e to the power g of x. We know f prime of x is equal to g prime of x times e to the power g of x. That's a known formula you can derive from the fundamental limit of calculus. And we're going to use that identity, you could say, for differentiation over here. Since we now have it in the form of e to the power some function, we can define our g of x to be that power over there, fn minus 1 of x ln of x. That is our g of x. And so now we have to differentiate this, which is our g prime of x. And with the product rule, again, like earlier, we know this is fn minus 1 prime of x ln x plus the derivative of ln of x, which is 1 over x times fn minus 1 of x. So let's write that down. F prime of n minus 1 of x times ln of x plus fn minus 1 of x times 1 over x, which is just divided by x. And so now we have our g prime of x. And now we can merge this with, which is, by the way, I want to express the power or the natural log of x is what gives us the fraction by its derivative. Now putting it all together, we know f prime of x is equal to g prime times e to the power g of x. We know f prime of n of x, we can write it as g prime of x times e to the power g of x. Now we can substitute what we have found so far. We've found so far that the derivative of x tetrated to n can be written as, let's see, the derivative of the previous degree, x tetrated to n minus 1 times ln of x, its derivative, plus x tetrated to n minus 1 divided by x, times e to the power g of x, which is e to the power fn minus 1 of x ln of x. There we go, ln of x. But note that this form over here, e to the power fn minus 1 of x ln of x, that is our original fn of x. So we can substitute that for our final representation of the derivative of x tetrated to n. F prime n of x is equal to fn of x multiplied by the whole factor of g prime of x, which in this case is f prime n minus 1 of x, which is the derivative of tetration x, or derivative of x tetrated to n minus 1 times ln of x plus x tetrated to n minus 1 divided by x, which is, I think, a cool little property. Ln of x, the inverse of exponentiation, division, the inverse of multiplication. I don't know, a very interesting formulation. But now we can substitute fn of x back to f of x. And we know fn of x is just x tetrated to n, which we denote this whole video in terms of the left exponent, which is my favorite way to represent tetration. It's straightforward, it's not complicated, but maybe latex users would argue otherwise. F prime of x is equal to x tetrated to n times x, the derivative of x tetrated to n minus 1 times ln of x. Let's get the exact formulation there. The x tetrated to n minus 1, that's clear, that's kind of legible. In terms of x, ln of x plus the actual value of x tetrated to n minus 1, which I think I should just write down here. The actual value of x tetrated to n minus 1 divided by x. And this is our derivative for x tetrated to n. And it's not a closed form, it's a recursive form because it's dependent on the previous degree. But yeah, thank you so much for watching.